Okay, so welcome everyone. It's a pleasure to have Jaroslav Trnka, who will give us a talk very early in his local time about the negative amplituhedron. So take it away. Thanks.
Okay, let me just, yeah. Okay, great. Thank you very much for inviting me to your seminar series. Yeah, and I will talk about some work from December and some work in progress with Nima Arkadi, Hamed Johannesen, and now also Dimitri Chicherin about amplituhedron, so some geometric picture which captures some information about scattering amplitudes in n=4 super Young mills. And our first attempt to do some resummation and calculate amplitudes at strong coupling. Yeah, this picture has been always at weak coupling. It was related to the perturbative expansion, but we found one interesting way, kind of purely mathematical. So far, there is no physics interpretation for that, how to use some approximation to do some all-loop order calculation and resum things to all loops. Okay, let me start slowly with some motivation, and then I will quite quickly jump into the actual topic. So, so one of the big questions are more philosophical, but also having like practical implication to search for new ideas is to describe in some new way what is perturbative S-matrix in quantum field theory, how to define it, and how to calculate it. And of course, there is a standard definition of scattering amplitudes using Feynman diagrams, and that's in every QFT textbooks. So if you have some process, you should just take the Lagrangian, derive Feynman rules, draw Feynman diagrams, sum all of them, and that's the result for the amplitude. Now, we have seen in last 20, 30 years that there are different ways how to calculate amplitudes, and they use different ideas. And these different methods, such as unitarity methods or recursion relations, or using integrability in certain theories, yeah, connection, yeah, many different ideas. Some of them work in specific theories. Some of them are more general, like these unitarity methods or recursion relations. They use certain properties of the scattering amplitudes and try to fix it from these properties rather than using the Feynman diagram approach, which is completely general. Yeah, it gives you a general recipe how to calculate amplitudes, but it often hides various things. Not only that it hides symmetries, sometimes they are not manifest in Feynman diagrams. We would call it hidden symmetries because they are hidden in the standard approach, but especially they hide simplicity of the final answer. So very often the final answer, it's much simpler than the individual terms which are in the expansion. And these methods exploited this simplicity and try to get the result more efficiently. Now in this talk, I will do a one particular direction in this effort, which is kind of the most extreme, because many of these ideas on the list, and there is a long list, try to use some physical properties of the S-matrix, some statements about singularities, different limits, symmetries, and so on to determine the S-matrix more efficiently. But with my collaborators, we have been interested in recent years in connecting the question about calculating scattering amplitudes to something kind of very alien from that point of view. And that's the connection to so-called positive geometry. So in this idea, the same thing that you get from the calculation using Feynman diagrams or these unitarity methods or anything else, you can also obtain from calculating certain differential volume forms on some geometry. And the geometry is fixed or is defined by some external data, which will be the spins and momenta of particles. They give the geometry for you, and then you should calculate something on that geometry. You should find some differential form. And this differential form gives you the amplitude. Or I will be more precise, it gives you the tree-level amplitudes or the loop integrand. And this is a general idea, but we have concrete realization only in a handful of theories, and the primary one is n=4 super-Young-Mills. Kind of the n=4 super-Young-Mills amplitudes are offered to us because they will correspond to the simplest possible definition of this differential volume form. But the general idea is that the geometry captures all singularities and all poles and all kinematical limits of the scattering amplitude. And then the differential form on this geometry is a way how to extract the amplitude out of it. Okay, so this is the Amplituhedron picture. So I will review it. That's the geometric picture for scattering amplitudes in planar n=4 super-Young-Mills. Now there are also extensions to other theories, to phi cube theory. But yeah, I will not talk about it, but there is a different geometry which lies behind it, but the logic is similar. But I will start from there. This is not what I will talk about mainly. I will start from there and do some twist. And in the Amplituhedron definition, we'll have something called positive geometry. There will be some positive conditions. Yeah, there's some positive inequalities. And I will define kind of an opposite of it, turning positive into negative. And I will show that it naturally defines a very related object to the scattering amplitudes, or to the loop integrand of the scattering amplitude. And that will be a logarithm of the amplitude to all loop orders. Now, this looks like just a small change. So instead of amplitude, I take the logarithm of the amplitude. But there will be a huge, it will be very important because the logarithm of the amplitude in general, the L loop amplitude suffers from IR divergences. But in gauge theories, the IR divergences exponentiate. And in n=4 super-Young-Mills, they take a particularly simple form. And the logarithm of the amplitude will have a very simple or very mild IR divergence. And starting from that, we would be able to define some IR finite objects by freezing one of the loops. Yeah. So I will describe what I mean by that. So we will define IR finite objects, and this will be exactly the thing that we would like to do, and we would like to evaluate this object. We will be not able to do it in general, but we will do it for some special class of geometry. So it would be some particular expansion of this object, but not in the loop, not the loop expansion. We will actually resum to all loops, but it will be some approximation. Now, this object already appeared before in the context of Wilson loops as a ratio of two different null polynomial Wilson loops. Yeah, I will describe. Yeah, I will mention what exactly it is. And there are some results for that at weak coupling and strong coupling, but the object itself is not known in general. Yeah, we will compare to what we get in our geometric approximation to the known results. Yeah, so this is one particular object we are interested in, but it's our first attempt to use this geometric picture to do some all loop order calculation, do the resummation, and look at the strong coupling, which is something which yeah, we were not able to do before. Okay, so let me just start with a few words about the loop integrand. So so for scattering amplitudes at tree level, these are rational functions of kinematics. But at loops, the amplitudes are more complicated. So let me first define the object I would like, which is the loop integrand. So normally when we talk about amplitude, we think about it as a sum of Feynman diagrams of some loop Feynman diagrams, when we are instructed to integrate over all loop momenta. Now, we can alternatively, that's what the unitarity methods do. Instead of summing Feynman diagrams, just choose some basis of integrals and basically expand the amplitude in this basis of integrals with some unknown kinematical coefficients. And then we should fix these coefficients by some means, for example, using the method of cuts. Okay, so this is So these are kind of the standard method for Feynman diagrams and the methods of unitarity. And these basis integrals are some box integrals, triangles, and so on in one loop, and more complicated integrals at higher loops. And there is some work. You have to find the independent basis, and then you have to fix the coefficients, which means solving some linear systems, very large linear systems of equations. But that's what people typically do. Now, something simple happens if we are in the planar limit. So if we are in the large n limit of gauge theories, we can sum all the diagrams together into a single object. The reason for that is that we can define global loop variables. And normally, each diagram, either Feynman diagram or this integral, has its own variables. Yeah, the meaning of the loop is specific to a diagram. Each diagram has its own loop. You have to specify where the L1, L2, and so is. And therefore, there is no meaning of going from one L1 in one diagram to the other L in the other diagram. But in the planar limit, there exist variables which you can globally define on all loops, on all diagrams. And they are called dual variables, and they are associated not with the edges of the diagram when the loop momentum is flowing, but with the faces of the diagram. And okay, but having this in mind, we can actually, in our operation for the amplitude, we can switch the integration with summing over all diagrams, and we can define a single rational function, which then we are supposed to integrate. But now we can talk about a single rational function for the amplitude, which is the loop integrand. Yeah. Now there is a question: is this function unique, or is there some total derivative we can add, and so on? That's a very that's an important question. In planar n equals 4 superamplitudes, this function is unique for symmetry reasons. Yeah, basically the symmetries of the theory doesn't allow us, once we fix the function, doesn't allow us to add anything else which wouldn't violate certain conditions. Yeah, but the important thing is that we have an object to work with, and this object is very nice because it's a rational function. It doesn't suffer from any divergences. It's well defined. Yeah, it only becomes divergent IR or UV in n equals 4 superangles, not UV, only IR, but in general theory also UV divergent once we integrate it. But before integration, it's a nice rational function of momenta, external and loop momenta. We can study. Yeah. Okay. Once we integrate our integrand, we get some complicated function, because the functions that we get in the loop integrals beyond one loop is in general unknown. Yeah, at one loop we know what type of functions we get. We get some dilogarithms, logarithms. We get some transcendental numbers, some zeta values. At higher loops, we definitely get some polylogarithms, elliptic polylogarithms, and so beyond. And the space of these functions and how to evaluate these integrals, it's a very open area of research. It's also a function of many variables, many cross ratios. So there are, it's a huge industry. But as I said, for us, we will focus on this first part, which is the loop integrand. And it's a rational function. It has many variables because if we go to arbitrary loop order, it depends on all these loop momenta, which on the left-hand side we would integrate over. Here we have them explicitly, but the advantage is that it's rational function, and we can basically determine it from its poles and singularities. Now there is a kind of link between the left and right-hand side, because the left-hand side are some polylogarithms which have branch cuts. The right-hand side is a rational function, so it doesn't have any branch cuts, but it has poles. And these two things are related on both sides. So there is a relation, but the precise relations to all loops is not completely understood. I would say it like that. When we do the actual calculation, I already mentioned that before, there is a problem with complexity. that in either method, you have a huge number of terms already for low loop order. Yeah, the number of Feynman diagrams just grows rapidly. And even in these unitarity methods, when you kind of reshuffle things and you do them efficiently, you still have this basis that you have to construct and then potentially integrate these terms. And that also, the number of terms in the basis grows very fast. But our way how to think about it, we will concentrate on this integrand, so we will not integrate anything. Despite I will give results for some integrated answers in the end, but they will be not obtained by integration, but by means of some differential equations. But we would like to really think about the amplitude as a single object, not as a sum of other things. Yeah, so it's a little bit change of paradigm, because this single object, amplitude, or the loop integrand more precisely, for us, this is the thing we would like to give a new interpretation to. And we would like to fix it by certain conditions. So it should be unique and fixable by certain conditions. Typically, we would use some physical conditions, as I said, as poles and singularities, because it's a rational function. Maybe we also need some various limits and so on to fix it. But the new idea would be to give some geometric interpretation of this object and fix it from mathematical conditions rather than physical conditions. And hopefully, or this, if successful, we will be able to define this object to all loops, define it. That would be the easier part, and hopefully use it to do some calculations. Okay, so let me now talk more specifically about n=4, planar n=4, just mention a few things. So here we calculate superamplitudes. So we define an on-shell superfield, which contains all the particles in the spectrum. It contains gluons, it contains some fermions, it contains some scalars. And then the superamplitudes in this theory basically breaks down into different sectors, in different helicity sectors, based on the SU4R charge. So you can just think about it in the gluonic sector. This just corresponds to different number of positive and negative helicity gluons. Yeah, so the amplitude can be also rewritten into sectors when at each level the gluonic amplitudes have certain number of positive and certain number of negative helicity gluons. That's one thing which we will use. The other thing is that there is a hidden symmetry in this theory called dual conformal symmetry, only in the planar limit. So as I said, in the planar limit, we are able to define these dual variables, which are global variables on all graphs. And the scattering amplitudes in this theory have, in addition to the normal superconformal symmetry of n=4, it has another conformal symmetry living in the momentum space. So there are two conformal symmetries. And yeah, it's okay. So this theory has a higher symmetry. Now, instead of yeah, so instead of using the standard variables, standard momentum variables, external momenta and loop momenta, we can use these dual variables, but it's actually just a middle step for us. From there, we change the variables once again, and we use something called momentum twisters. So all data, all external data, and also the internal data, the loop momenta, will be labeled, or the information will be stored into points into z's, and each z is a point in the projective space V3. Yeah, and it contains, you can just think about it as a change of variables. Instead of momenta, I will use some twister variables. The advantage of that is that they make manifest this hidden dual conformal symmetry. So it's easier to write the expressions which are dual conformal invariant, while in the original picture of momenta, this is a very non-trivial condition. Here it's completely manifest condition, because the dual conformal symmetry acts as a simple SL4 on these momentum twisters. So then I will write some expression. They will be all written using these momentum twisters, but this is nothing else than the change of variables. Yeah, and like the dual variables, these momentum twisters are also global variables. So you can define the same variables for any term in your expansion, and then you are able to sum them into a single thing. Now, there is one thing special which we will not really kind of exploit here, but I just want to mention it. Why is planar n equals 4 integrand special? So it's this hidden symmetry which makes it special. We will see kind of a mirror of that on the geometric side once we start to talk about the geometry. But there is kind of a physics perspective why it's special. And that's because it has all the dynamics, all the physics happens in IR. We know that the theory is UV finite, so it doesn't have any UV divergences, but this is also imprinted in the structure of integrand, where you never have any pole which sends the loop momentum to infinity. So typically, for the loop integrand, you have poles in IR. I would call it in IR. So these are the poles when the propagators go to 0 in Feynman diagrams or in some integrals. And you have also poles when L goes to infinity. And yeah, and they are kind of an imprint of some UV structure there. But in n equals 4 super-Yang, there are just no such poles. And this is one of the implications. This is one of the consequences of the dual conformal symmetry. So everything, all the poles are in IR. Yeah, all the poles are just factorization poles and soft collinear poles. There is no.
Is this just the same as
happening?
So, sorry, just a quick question. So is this just the same as the integral not having a UV divergence, or it's a strong?
It is more. It is a little more than that. Yeah, it's interesting. It's not completely kind of definitely if it doesn't have UV divergence, it doesn't have any poles at infinity. But there are integrals which are finite, like a triangle integral at one loop, which has poles at infinity. Yeah, right. It's just that these poles don't generate a divergence. Yeah, they are kind of not strong enough. Yeah, the singularity at infinity is too weak, and it doesn't generate a UV divergence, but there is, for example, for this triangle integral. But in n equals 4 super-Yang, there are no such poles. Yeah. Yeah, note that this is little more than sending L to infinity because, yeah, the pole at infinity may be, for example, at some complex momentum. Yeah, you have to first cut propagators and then send L to infinity. At that point, your L, your loop momentum L, is already complex. So you are not integrating over that loop momentum. So you will not generate, it will not materialize into a UV divergence, but it is still there as a residue of the integrand. But in n equals 4 super-Yang, there is no such a pole, yeah, period. So it's stronger than UV finiteness, but what precisely it means for the final amplitude, how is it imprinted in the final functions once you integrate, that's not clear, yeah. But there is definitely some condition. At the level of symmetries, this is a consequence of dual conformal symmetry. Okay, so now, when I said something about this dual conformal symmetry or the superversion, dual superconformal symmetry, they close together with the ordinary superconformal symmetry into an infinite dimensional Yangian symmetry. Now, the thing which is invariant under this symmetry is a 3-level amplitude and loop integrand. Now, these symmetries are broken once you integrate the integrand because it's IR divergent and the choice of regulator breaks these symmetries. There are some attempts to define a regulator which will not break at least some of these symmetries, but in general, if you use DIMREG, for example, it breaks all the symmetries. But yeah, but presumably in some very controlled way. In any case, one thing is that the object which is actually invariant under these symmetries is not the amplitude itself or the loop integrand itself, but you have to strip off some factor called Park-Taylor factor. It's an simplest 3-level amplitude. And after you strip it, then the remaining object is invariant. And for example, we can write it using these momentum twisters. Yeah. So this is also the subtlety of the dual conformal symmetry, why it's harder to see it directly, let's say, in the n equals 4 action or in some other context, because there is some operation that you have to do on the amplitude to expose it. Yeah, the amplitude is not directly invariant. Okay, now in the following, we will consider the simplest amplitude called MHV. So this is in terms of this helicity sector. This K index was the number of negative helicity gluons. We set K equals 2. And in that, for that amplitude, the factor that we are stripping off is directly the 3-level amplitude. So if we do the perturbative expansion, as you see in the bottom, it starts with 1. That's a 3-level. And then it has a corrections with 1 loop, 2 loop, 3 loop, and so on. Okay. Now, yeah, the loop integration is very difficult. We get some complicated transcendental functions. Now, the amplitudes are IR divergent after we integrate, so we have to use the regulator. But there is something simple about the IR divergences because they exponentiate. So if we write an amplitude in this way and we integrate it depends on the regulator. So let's just choose the dimensional regularization. But once we resum it, the leading divergence piece has this structure. So it's an exponent of 1/epsilon² times some a priori unknown function of coupling plus some corrections, things 1/epsilon and finite corrections. Now, in N=4 super Yang-Mills, we can actually say something even more about the finite pieces. This is called BDS-Ansatz. For 4 and 5 points, this information is kind of, there is a definite statement. For 6 and higher points, there are some finite corrections which, which are unfixable just from the symmetry, because that's the way how they fix it, basically, from the dual conformal symmetry. Yeah, it doesn't mean that the amplitude is known, but kind of the kinematical dependence or the dependence on the kinematics is trivial, but there are still some unknown functions of coupling. Yeah, for example, this FG, and we will talk about it much more later. Yeah, so once we take the logarithm of the amplitude, so this is just a convenient thing to do, then the logarithm of the amplitude has only this mild divergent 1/epsilon². Okay, and the thing that's sitting in the numerator, the non-trivial function, we can kind of we can capture, or we can put together in a function of coupling called cusp anomalous dimension. Yeah. So this is an expansion of the coupling, which has some numerical factor in front of every power of g, or g². And this function is a priori unknown or not calculable from the point of view of scattering amplitudes, because that would require calculate the amplitudes to all loops. But this function is actually calculated or predicted by integrability, by the Eden-Staudacher equation from a completely different point of view of spin chains. Yeah, it's most likely correct that the function they calculated is the function that is in the amplitude of N=4 super Yang-Mills as controlling the leading IR divergence. It's still kind of, there is no official proof, but there are a lot of tests, and yeah, everything confirms that. Yeah, there are low loop order tests. People calculated amplitudes up to 4 loops. They saw that they exactly match with the gamma cusp calculation from integrability. But one of the kind of things that we would like to understand, one of the motivations, is actually to, well, derive this answer for amplitudes, but also see how the integrability is encoded in the structure of scattering amplitudes. This is something which is not clear for, it's not clear how the integrability of planar N=4 super Yang-Mills we can see in amplitudes. Yeah. Okay. So yes, so this is my shopping list. I would like to do. I would like to determine the integrand to all loop orders, which is a very hard question, but we will do it in one particular situation. We would like to integrate it or calculate it by some other means. We would like to resum it to all loop orders, and we would like to extract the IR divergence from that and go to strong coupling and make some connection to these integrability results. Okay. So any questions before now I start with kind of switching the gears completely and starting like a different path from the point of view of geometry?
Just to recall, maybe the result you stated from Staudacher and Beiser, it's proved for the anomalous dimension of the cusp Wilson line, right?
Yes. Yes.
And so what is conjectural is the duality between the amplitude.
Right. Yeah. So yeah. Well, it's also not calculated from the Wilson lines, but No, I would say that, yeah, it depends what you mean by proof. Yeah, it's not that you are doing calculation with Wilson loops or with amplitudes and you get this, you are not able to reproduce that result, but yeah, there is a strong evidence. I would call it a proof, yeah, but we are not seeing this directly going from amplitudes, yeah, or calculating Wilson loop to all loops. Also not that, we don't have these results, yeah. Yeah, I would say it is proven, but we need a more insight or evidence from the point of view of amplitude. Yeah, and as you said, this is something I didn't mention. There is a relation between the correspondence between the Wilson loops and scattering amplitudes. And yeah, we also have proof. Yeah, we don't have a formal proof that this is correct, or we have a strong evidence or almost a proof. Yeah, there is a proof at the level of recursion relations. Both objects satisfy the same recursion relations, so we can perhaps call that it's proven. But yeah, I would say that it would be good to have like some definite confirmation that all these correspondences are correct. Yeah, but even if we take for granted that the gamma cusp is calculated from integrability, which I take, yeah, I'm perfectly happy with that. Yeah, we would like to see it emerging from amplitudes. Okay, so now with the
can you also ask, sorry, before you continue, just a very broad, bit of a general question. So you're using all this special magic specific to 4D and n equals 4, but then you are regulating, you're doing dim reg, so these things, they commute for the observables that you are considering, or should one worry?
Yes, so I would like to calculate this integrand, and there is no subtlety. This is a rational function. Yeah, so this integrand I can calculate. I can sum Feynman diagrams. I can do something else. I can use these unitarity methods, and here I will do it in a different way. I will use this positive geometry. This would be conjecturally, because officially I cannot prove it. I'm doing some calculation using some volumes of some geometry or some differential forms. And this integrand is well defined. There is no subtlety. Once you start to integrate, you have to choose a regulator because the thing is IR divergent. So I have to choose a regulator, and yeah, and I will do it, for example, in the dim reg. Now, if I choose different regulator, then the finite pieces would be different. Yeah, the leading divergent piece will be the same, but the other pieces are different. So yeah, so in order to calculate the amplitude, I have to break the symmetries. Yeah, I have to do something violent to it. Yeah, so therefore that's the reason why the integrand is such a nice object, because it doesn't suffer from any of these problems. But in the end, yeah, if you want to calculate the amplitude, you have to kind of break all your symmetries. Now, of course, there are attempts to not to break the symmetries, find some regulator which would preserve the symmetries. But yeah, I would say that this is like an open question. Yeah, something was done at one loop and two loops, but yeah, it's not remotely done. Yeah, so I agree. Yeah, in the end, but once we do everything in dim reg, for example, then this is a good regulator. Yeah, it regulates. So if we do everything consistently in dim reg, yeah, we are getting the answers in dim reg. Yeah, so this calculation is in dim reg. And you can calculate the 1/epsilon piece as well. You can calculate the finite pieces, but they do depend on the regulator then. Yeah, not the leading piece, but the subleading do. Yeah. So what shows up in 1/epsilon piece would depend on if you choose dim reg, or for example, there is a mass regulator. You can go to the Coulomb branch of n equals 4. You can give masses to scalars, and that also regulates these masses. Yeah, but yeah.
Okay, thank you.
Okay, so yeah, so now we define the positive geometry. So this is so now very generally we would like to define some geometric space, which is labeled by some parameters xi, and the space is defined by a set of inequalities. So there are some polynomials when we say that our parameters, let's say x1, x2, x3, satisfy these inequalities, and that defines some region in the space. And once we have this space, we can define a differential form, omega, and the differential form will have special properties, because if you go to any boundary of this space, which is labeled by saying one of the variables goes to 0, it generates a logarithmic singularity. So the form goes like dx over x when x goes to 0. And this must be true for all boundaries and even all boundaries of all codimension. So if we have the higher dimensional space and we go to first boundary, second boundary, third boundary, going down and down, then we always have to generate this logarithmic singularity. It must only behave like dx over x. It can never behave like dx over x squared, for example. So the simple example of positive geometry is just 1D interval. So if we have a semi-infinite interval, which is that the positive geometry is just defined by x bigger than 0, and then the logarithmic form is just given by dx over x. Dx over x is posed at 0 at infinity. That's exactly what we needed. Now we can have a little more complicated 1D interval, which is bounded by x1 and x2. So this is how we would write the positive conditions. And then the differential form is following. It has two poles at x is equal to x1 and x is equal to x2. And then has also some numerator factor, which guarantees that if we take a residue on x is equal to x1 or x is equal to x2, we get 1. Yeah. So once we go here, it's just one dimensional, but once we take all the residues going to 0-dimensional space, we should get 1 from the form. Okay, so this is the form that we associated with this 1-dimensional space. We can go to 2 dimensions. For example, if we have a positive quadrant, x and y go from 0 to infinity, and the form is just dx over x, dy over y. Again, very simple. But we can have something like a triangle in the positive quadrant. And then, yeah, we would have to first define the triangle using these inequalities. X and y are both positive, plus this extra condition must be positive. And yeah, and then from that, we can write, again, the differential form, which has these logarithmic singularities on all boundaries. And now it's a 2-dimensional thing. So these singularities must be there for codimension 1 and also codimension 2 boundaries. You can see that in the denominator of the form, you always have the first boundaries, because these are the things that you can immediately set to 0. You can take a residue on them, which then means going on that boundary and evaluating that form on that boundary. Now, the general, so here it looks like that the only thing that I need to know are boundaries. So if I know boundaries, I'm always on the right side of the boundary. So I write an inequality for that, and that defines the geometry. Now, this is not always true. And in the cases we are interested in, it's indeed not true. And this is where the Grassmannian enters, when we need more conditions than just boundaries. So let's now consider just the space of 2x4 matrices modulo GL2. So this is a Grassmannian G2 form. It describes a 2-plane in 4 dimensions. And there is a positive part of this Grassmannian, which says that all 2x2 minors are positive. So these are our positivity conditions. So the real Grassmannian doesn't have any boundaries. Yeah, it just has, yeah, it's a matrix with some entries. These entries are unfixed. Yeah, they can take any values. So that's not an interesting space. But if we put this extra structure saying that the minors are positive, we get a space with boundaries. And now the thing is that despite we have to impose all these minors being positive, not setting any minor to 0 is a boundary. Yeah. So for example, setting minor 1, 2 to 0 is a boundary, but setting minor 1, 3 to 0, despite we have to impose it as a condition to define the space, it's not a boundary. It's not a boundary of the space. And that can be seen from just some simple identity between minors, because the product of the minor 1, 3, and 2, 4 is equal to the sum of these products of minors 1, 2, 3, 4, and 1, 4, 2, 3. This is just a Schouten identity. And we cannot set 1, 3 to 0, because if we set it to 0, the left-hand side is 0, but the right-hand side is a sum of 2 positive things, because by definition of the space, all the minors are positive, and the 0 cannot be sum of 2 positive things. So it's not a boundary. However, we still have to impose that condition to define the space. Okay, so this is a new feature that, unlike in these examples, and actually the example of any polytopes, then not just boundaries are enough. We have to define it. We have to say more. Okay, now this positive Grassmannian G24 would be actually very useful for us.
Sorry, if I may ask.
Yeah.
I mean, I don't see what is wrong about just choosing just the right number of minors such that you get everything, and then I would call them just my condition, and they're all boundary, right? Because as you just said, 1, 3, 2, 4 will always be positive, or no? You mean because they could be both negative?
Yeah, they can be both positive or both negative.
Ah, okay. So that's a
so it cuts this. Yeah, that's a regular question. It cuts the space into half, and you just want to take 1/2 of that space.
Okay, so you still have this ambiguity to fix things.
Yeah, so you have this ambiguity which you have to fix. Yeah. Therefore, you have to say that they are all both positive, despite it's not a boundary. Yeah. Okay. So let's look at this case in more details because we will actually use it. It's a 2x4 matrix. Fixing the GL2, we can fix GL2 in any way we want, but we just can fix 2 columns to be a unit matrix. So we are giving a parametrization for this positive Grassmannian space. So this is one particular choice. So you can see that the matrix is labeled now by parameters x, y, z, w. And once we impose that all the minors, 2x2 minors are positive, this just fixes x, y, z, w to be all positive. So this is our positive geometry. This is our space. It's a space of all these matrices where the parameters x, y, z, w are all positive. Now the boundaries of this space are setting minors 1, 2, 2, 3, 3, 4, or 1, 4 to 0, which sets one of those 4 parameters to 0. Yeah. So yeah, that's a boundary of the space. And yeah, if here I fix the minor 1, 3 to 1, so obviously it cannot descend to 0, but you can also see that minor 2, 4 is the sum of 2 positive things. Yeah, xz plus yw. So I also cannot send it to 0, but it was important that I impose these conditions. Now the logarithmic form on this space is really trivial because we just have 4 parameters being positive. So it's the logarithmic form is just dx over x, dy over y, dz over z, dw over dw. But this was in some particular parametrization. So I can kind of undo that parametrization and I can write in invariant form without fixing the parameters. And it has this form. So it has these 4 minors in the denominator, 1, 2, 2, 3, 3, 4, and 1, 4. And it's a form in all parameters of this matrix modulo the GL2 redundancy. Yeah, so I just write it in that way. If I choose the parametrization that I did here, it just turns immediately in this form in terms of x, y, z, and w. Okay, so why I did say that? Because the loop integrand in planar n equals 4 superdiagonals can be also parameterized by a set of parameter xi, yeah, similar to these ones. Now, this is a very surprising statement about n equals 4 superdiagonals. So this is very specific to n equals 4 superdiagonals, but all the singularities are logarithmic. Yeah. So we can also think about the integrand as the differential form with d-log singularities in the same way we started to do it from the point of view of geometry. Now the question is, can we connect these things together? Is there any positive geometry which differential form would give us loop integrand in n equals 4 superdiagonal? Yeah. So the logarithmic singularities are on both sides. Now for n equals 4, this is not something which you can derive from symmetries, or this is not, it's kind of a hidden property of the theory, but yeah, it is there. So that's the reason why we can make a connection to the geometry. But it's still the question, is there any geometry which realizes the integrand? Okay, so I will not talk about the amplituhedron in complete generality because there is a lot of language I would have to introduce, and so I will look specifically at the case of 4-point amplitudes when things will be very simple. Yeah. Now, so the amplituhedron picture is for the loop integrand, and the result of that is some d-log form. And again, if we would like to get the amplitude, which is IR divergent, then we have to do all this extra treatment. We would have to integrate it. Now, the starting point is setting the kinematical variables. So we use these convenient kinematical variables, which are these momentum twisters. For 4 points, we have 4 external momentum twisters, Z1, Z2, Z3, Z4. So these are points in P3. You can think about it as just 4 vectors, but they live in the projective space. And this is where the external momenta P1, P2, P3, P4, and the information about helicities goes. It goes into these momentum twisters. It's a change of variables. Now the loop momentum is different because that is off shell. Yeah, the external momenta are on shell, but the loop momentum is off shell. So it's not in momentum twister space, it's not represented by a point, but by a line. So the loop momentum is a line in P3. Now, there is some positivity condition part. There is a positivity condition on external data and on this loop momentum AB. Now, because at 4 point, that's the reason I chose 4 point, this positivity conditions on external data is trivial. We have only kind of one condition that we impose, is that these Zs are 4-dimensional. So the only kind of invariant we can make from them is a 4x4 determinant. And this is what we denote with this bracket, with this angle bracket. These are 4x4 determinants of the Zs which enter the bracket. And here we have only one, and we just have to say that it's positive. Now, the information about the external data is completely trivialized for the 4 point case, and everything is about this loop. So everything is related to the loop and what are the conditions on the loop AB. So we would like to restrict it to find the geometry for AB. And the amplituhedron is indeed, in this case, the configuration of all lines AB, which are allowed. And on this configuration space, we then want to find this logarithmic form, and that would be the loop integrand. Now, the one loop amplituhedron is defined in a following way. It's a configuration of all lines AB, which satisfy these conditions. Yeah, so these 4 brackets, which are these 4x4 determinants, must be positive, including the AB13 and AB24, which must be negative. Yeah. So parametrizing AB, we get conditions on the parameters of AB. Yeah, and this is our positive geometry. So here I use certain parametrization. When I expand the A and B, the A and B are 2 points on a line, 2 arbitrary points on my line AB. I can expand them in terms of some basis of these 4 momentum twisters with some parameters. So everything now boils down to these parameters. And this positive space reduces just by to the space of X, Y, Z, and W being positive. So again, it's a very simple space, and it has a very simple form. Again, the same trivial form. So this is in parametrization. I can then go back from the parametrization to the unfixed form written in terms of these 4 brackets, and I get this form. Note that this is just a momentum twister version of a box integral. Yeah. So this thing can be written back if you want in terms of just ordinary momentum variables. And this is just a box integral. And indeed, the n equals 4 super-Yang-Mills integrand, planar integrand at one loop is just a single box. Yeah. So this is what we get as a logarithmic form, but it is a particularly simple case. Yeah. However, this continues to higher loops. So we, at 2 loops, we have configuration of 2 lines, AB and CD. Each of them corresponds to 1 loop momentum. And the geometry of the space is defined in a following way. Each of these lines lives in the 1 loop geometry, in the 1 loop amplituhedron. Now, if nothing else is imposed, so this restricts the parametrization of these 2 lines. If nothing else is imposed, we can write the geometry, we can write the logarithmic form, and we would just get a product of 2 1 loop objects. So this would be a 1 loop square integrand. Now, in order to make it a 2 loop integrand, we have to impose an extra condition which entangles these 2 loops together. And the condition is that the 4x4 determinant of A, B, C, D together must be positive. So while the initial conditions for each loop were just linear, like even trivial, just setting that the parameter is positive, this quadratic condition between the 2, there is this extra condition between the 2 loops is quadratic. So this makes the space more complicated. And yeah, indeed, the form is also less trivial, but we can take this space. So this is a set of 9 inequalities on 8 parameters of the space. 8 parameters parameterizing on 2 of these loop momenta, A, B, and C, D. And we can find this form. Yeah, so we have to triangulate the space. There are some ways how to do it. We have to triangulate it, and then for each term in the triangulation, write the forms, sum the forms together, and find the logarithmic form on this whole space. And anyway, so the form looks like this in this parametrization. If we change back from these parameters back to the A, B, and C, D, which are these loop momenta written in momentum Pfister space, we get a sum. We can interpret it as a sum of double box diagrams plus cyclic friends. Yeah, so we can see here explicitly that it gives us the integrand of 4-point amplitudes in n equals 4 superangles that we know. Now, at L loops, we have the positive geometry is a configuration of L lines. Each line is in the one loop amplituhedron. And then for any pair of two lines, we have an extra quadratic condition. So in our usual parametrization, you see what are these conditions. Now, this is a definition of the loop integrand to all loop orders at 4 point. However, if you want to actually find the form, you have to solve these inequalities. And it's a very complicated set of inequalities. But it should be, because it captures all the complexity of the L loop integrand. If you do it the usual way, let's say in terms of the Feynman diagrams and in terms of the unitarity methods, you would just sum infinite number of diagrams, yeah, which are very complicated, diagrams like that and many others. So the complexity goes into the complexity of the geometric space. Yeah, so the physics question of summing these diagrams turns into a mathematical question of triangulating this space. Yeah, basically solving quadratic inequalities, a lot of quadratic inequalities. There is L choose to quadratic inequalities and L loops.
So yeah, just to say that you have 5 minutes of your official time.
Okay. Yeah. I will try. Yeah, I will now go immediately to the negative part. Yeah, hopefully it will not take so much. Yeah. So the big open problem here is how to triangulate the space. So how to solve the problem of 4-point scattering to all loop orders and get some exact result for the loop integrand. Now, we don't know how to do it because this is just a complicated problem, triangulating that space. But yeah, we know how to do it for certain cases, for certain cuts, when these quadratic inequalities turn into linear inequalities, then you can do it. Yeah, you have to send some of the parameters to 0 in order to simplify the inequality. Okay, but now I will turn to the question of negative geometries, and where we will be able to do something interesting with that. So I will introduce a graphic notation. So for each vertex will be a loop. And so this is just denote what geometry I'm talking about. So each vertex, when you see in the picture, is a loop. And each blue dashed link is a mutual positivity between two loops. So each loop is a one loop amplituhedron, and each link is saying that A, B, C, D is positive. So they are kind of connected by a positive link. So the L loop and the picture will denote the D-log form, the logarithmic form on this geometry. So this will be my notation. So if I talk about the L loop integrand, it's a D-log form corresponding to the complete graph of L dots, of L vertices. Yeah, because the positivity conditions is between any pair of two of the loops. But now let me introduce a negativity conditions, like as a complement to the positivity one. So now the ABCD is negative, and I denote it by a red link. Yeah, so the red link is negative, the blue dashed link is positive. If I take a sum of these D-log forms or a union of these geometries, it's a condition. There is no condition on ABCD because I'm taking union of positive and negative, which means no condition. Yeah, and this is a simpler space. Yeah, because in particular here, the thing on the right-hand side is a product of one loop objects, while on the left-hand side, these are two loop objects. Now, the idea is to express all positivity links using negativity links and empty and no links. So this is just a geometry problem, nothing to do with amplitudes. So I take a completely connected graph and replacing each positive link by these negative links, I get a sum of other graphs with only negative links or no links. Yeah. For example, for L equals 3, where you have free loop problem, which means 3 dots this sum will be following. Yeah, so there will be a graph with no links, then 1 link, 2 links, 3 links. Okay, now I can write a formal sum over all the loops, which means I can take this object on the first line. I can dress it with g to the L. Yeah, I introduce a coupling constant and I raise it to the loop order, to the number of the dots, and I sum from 0 to infinity. Okay, so this is just a formal object at the moment. Now, because of the properties of the graphs from the graph theory, the ones on the right-hand side, these things exponentiate. So I can actually write it as an exponent of only connected graphs. Yeah, before it was all graphs here, and here it's only connected graphs. Yeah, and I can take a logarithm of both sides and expand in G. Okay, so I have a logarithm, I have an L loop logarithm of the amplitude, and this is a sum of all connected graphs with L vertices. Yeah, okay. So this is a new expansion for the logarithm of the amplitude as the D-log forms of some positive geometries, so negative geometries. Yeah, so the space of L loops with some negative conditions imposing between them. Now, why this is, so maybe I will go here quickly. Why this is important? The important thing is that the negative geometry basically tells us that there are very mild IR divergences once we integrate that form with some regulator to get an integrated expression. Yeah. So the negativity conditions between these loops doesn't prevent the loop to have access to collinear and soft collinear regions, which generates the IR divergence after we integrate. So it doesn't have these singularities. Okay, so there is some formal way how to say it. If we would like to generate the IR divergence, we would basically have to go with all loops into a collinear region at the same time, and this generates only a very mild IR divergence. So while the general L loop amplitude has a divergence 1 over epsilon to the 2L, these objects have only divergence 1 over epsilon squared. And that we know because the logarithm of the amplitude also has only 1 over epsilon squared divergence. So knowing that, we can actually define an IR finite object. The way how to do it is here. We can, the object after integration has 1 over epsilon squared divergence, but in order to generate this divergence, we would have to integrate all of the loops. Yeah, if we leave one of the loop unintegrated, the object is finite. Okay, so okay, so this is this object F. So we defined a IR finite object, which is taking the logarithm of the amplitude and integrate only L-1 of the loops, not the last loop. And this object is finite, is an object of a single cross ratio for 4 point. And this is the one which we take and expand in terms of these negative geometries. Okay, so this, the expansion, so here this cross means that this is a frozen loop. This is the one we are not integrating over. And the thing on the right-hand side is an expansion in terms of all geometries that we get in our expansion. Now, each link here means a negative condition between 2 of the loops. Now, there is some hierarchy of these graphs. You can see that some of the graphs are like tree graphs, some of the graphs are loop graphs, but they are all at the same loop order because the number of loops is just given by the number of dots here. But there is some internal hierarchy of these graphs, which has nothing to do with the loop expansion. They have all the same number of loops. But in this space of loops, there is some hierarchy, which we will see will be very important. Okay, now let me note that this object F has been already defined before in the context of Wilson loops. It's a ratio of 2 null polygonal Wilson loop, one with the Lagrangian insertion at the point x0, and the point x0 is exactly corresponds to the loop that we are not integrating over, the AB, we call it AB0. It's a function of a single cross ratio. Yeah, it has this connection to the Wilson loops. Now, this object is not known to all loop orders, but there are results at weak coupling and results at strong coupling that were calculated. Yeah, so there is a connection to the thing that we defined, to the thing that was studied already before. Now, going to these graphs, we can see that if we can actually do the integral, we can integrate it. It's a function of single cross ratio, which makes the integration simpler. And we can see that the graphs, which are tree graphs, look much simpler after integration than the one which has this loop. Yeah, note that these L equals 3 things are all of the same loop order. Yeah, but you can see that the tree graphs in our way how to expand it using these geometries are simpler than the loop graph. The loop graph is more complicated. Yeah, the tree graphs are basically only the powers of log square and pi's when there is some Li4 here for the loop graph. Yeah. So this motivates us to just say, well, maybe we will be not able to calculate these integrals to all loop orders and sum it and get this function f in complete generality, but we can do restriction in our geometry, take only simple geometries and try to integrate only those and sum them and look how good approximation it is to the full function fgz. Yeah. And okay, so yeah, because I am already over time, let me just say what this approximation is. Well, the approximation is that the only graphs that we take are the tree graphs in our notion of what the tree means. Again, these are still loop integrals, but as these negative conditions are, they form a tree graph. And one good thing about it is that we know how to calculate the integrand for that to any graph. Yeah, we don't know how to do it in general for the loop graphs that I have here on the right-hand side. Yeah. So even the special class of tree graphs are ladder graphs. So only the graphs which look like ladders. So we can dress them with the coupling and we can resum them. Now at each loop order, there is only one graph. Yeah. And then we found some differential equation, which applying of this function on the left, which is a function of coupling and this cross ratio z. This satisfies the differential equation, and one can solve the differential equation and gets a particularly simple form of as a function of z. Okay. Now for the tree graphs, so if it is not just ladder by an arbitrary tree, we still can find the differential equation. For that, we have to define some generating function, but there is also the same differential equation applies when the differential operator basically removes one of the legs and gets a tree graph with one lower number of vertices. It's a more complicated system, but it is solvable, and we can find the closed form for the full function f3 gz, but there are some constants which are implicitly defined by some equations that we are not able to solve, but we can always solve it numerically. Okay, so we get, so there is this function fgz, which is not known in general. We found these two approximations depending on which graphs in our geometric expansion we took. We either took only ladders, which is the simplest, but we were able to solve for it completely, or we also took the trees, which is a more complicated, richer expansion. And we also solve for that a little bit, not explicitly, because there are some constants defined from some equations we cannot solve explicitly, but we can always do it numerically. Now, having these two functions, we can go to the strong coupling. So that's the thing we wanted to do from the beginning, to see any strong coupling result coming from these geometries. And also we can find the contribution to the cusp anomalous dimension. Okay, so let me mention here that if we only take ladders and go to the strong coupling, they are exponentially suppressed. Yeah, which is actually not the right behavior of this function at strong coupling. Now, these ladders behave the same way as the actual ladder integrals that we can resum. So that was already done in the past. You can take the ladder integrals just in phi cube theory, dress them with coupling and resum them, and look how they behave at the strong coupling, and they would behave in a very similar way. Our geometries are not ladder integrals. Yeah, they have nothing to do with them. but they behave the same way at strong coupling. And they are not the good approximation to what the planar n equals 4 super-anomalous result should be. So the letters is a not good approximation for this function. Yeah. This is just saying that there is some similarity between ladder integrals or ladder geometries, but yeah, they are not the same. Now, what is the actual behavior of this function f at strong coupling? It's linear in G at strong coupling. Yeah. So unlike these ladders, which are exponentially suppressed, the actual function is linear in G. So it's linear at strong coupling. Now we can do this expansion with our F3, yeah, so with our tree approximation, and we find that it's constant at strong coupling, but it has a 1/G expansion. So we are missing the leading piece at strong coupling, but it has qualitatively the similar behavior. It's not exponentially suppressed. It has 1/G expansion, but it's constant at strong coupling. Okay, so the graphs that we took definitely they don't capture the leading behavior at strong coupling. However, the surprising thing is about the gamma cusp. Okay, so the gamma cusp is this object which shows up in the logarithm of the amplitude. And actually, it was shown that it can be extracted from this function f that we define. Yeah, so it is related. It is very closely related. This function f has more information because it's a function of g and the cross ratio z. But you can extract the gamma cusp as a function of g only from this function. So we can try to do it now. So for the ladders, we get even a closed formula. Remember, the ladders were not capturing correctly the full function f of z at strong coupling, but we can nevertheless look what is the gamma cusp coming from these ladders. And surprisingly, it looks very similar, or it is exactly the same as something called gamma octagon, which was calculated also by Benjamin, Lenz, and others in a different context. Yeah, this gamma octagon controls the 6-point remainder function in some particular limit, and we have the same function appearing here as the gamma cusp related to these ladder integrals. Okay, now we can look at trees. We saw the trees was a better approximation, which makes sense because it was a collection. We took more of these negative geometries diagrams. Yeah, so there is some particular calculation. We can find a differential equation for the gamma cusp coming from these trees. Yeah, we cannot solve for it explicitly. Again, there is some formula that we cannot invert, but we cannot solve it analytically, but we can do it numerically. And so this is the result. Yeah, I'm sorry, I'm really over time, but this is one of the last slides here. So let's now look at really how the gamma cusp looks like. So this is the true gamma cusp on the first line. This is the expansion at weak coupling. That's the first line. It goes like g squared, g to the 4. There are some zetas and so on. And this is an expansion at the strong coupling. It starts as a g, then there is a constant. There is a 1/G, 1/G squared, and so on. For the ladder, this is our this is the approximation taking only one graph at each loop order. So this is a very cruel way how to cut all the graphs. At weak coupling, at weak coupling is kind of trivial. We are getting the right answer up to certain order, then we are missing some of the graphs. At strong coupling, we are getting a G term. So we correctly, at least qualitatively, get the right behavior at the strong coupling at the leading and subleading order. Different numbers, so we are missing something, but then it has an exponential suppression. So it's not, there is no 1/G expansion. So at strong coupling, it captures something, but then there is no 1/G expansion. So it is less non-perturbative than the default result. Now for the tree, we get a 1/G expansion. Again, we are getting different numbers because we are missing these graphs with loops, these loops of loops, but there is a 1/G expansion at the strong coupling. So qualitatively, it captures the behavior well. Okay, and there is some comparison at low coupling. So let me conclude here. So we were interested in the logarithm of the amplitude, in the gamma cusp, and in this finite object. we use this approximation to calculate it. Yeah, we were able to define just geometrically what this object is as a sum of these negative geometries, but they were too complicated for us to integrate. Yeah, because in the end we really wanted to integrate, we use these geometric approximation that we only took the ladders or the trees. In that case, we were able to evaluate them, resum them, and go to the strong coupling, and then we compare to the results which are in the literature. We are definitely not getting the right answer because we are missing all the graphs that we ignored, which had these internal loops. But surprisingly, for the gamma cusp, the behavior was qualitatively correct, despite, of course, the details, the particular constants are different. So now the main question is what these loop corrections are. Again, these are not loops in the traditional loop sense. They are just more complicated geometries. Yeah. So there is a surprisingly some other expansion of the amplitude, not in the loop, not in the coupling, but it's some like complexity of these individual terms in the geometry. And we did just the leading order. So the question is what happens at the next order. Okay, let me stop here. Thank you.
Okay, let's thank Jaros. Very nice talk. So we have time for a few questions.
Okay,
go ahead.
Yeah, well, you call this an approximation, but if I understand, it's more like you choose a diagram which are simple enough so that you can deal with them, and it's just a subset, but there is no reason for them to dominate in any sense, right?
No, there is no reason for it. Yeah, that's a good point. Yeah, there is no. We just took them because we were able to calculate them. There is no reason for them to dominate. Yeah, if we go back to this expansion, yeah, they are just The first part was just a graphic representation. So these are different graphs which contribute. We rewrote this one graph in terms of many graphs. Yeah, this was kind of this thing of doing it, but there is no hierarchy on the right-hand side. For us, geometrically, there is a hierarchy because more links you have, more conditions between this A, B, and CD you have, more complicated the geometry is. But this has nothing to do with the loop order or coupling or anything. Yeah, it's just the level of complication. Yeah, but it seems that there is something in it. Yeah, because if we look at these, we see that the trees are simple and the loop is complicated. They are of the same order. They are two loop integrals. They are L equals 3 because we are not integrating over one of the loops. But there is some hierarchy between them. And then we just this ad hoc thing. We said, well, let's just take the simple ones and ignore the complicated ones. Of course, as the number of graphs, there will be a lot of these loop graphs. So the number of these tree graphs is minimal. If you go to infinite L, just these loop graphs should dominate. Yeah, because everything has loops. Yeah, there is just minimal number of these tree graphs. But still, surprisingly, this is some approximation which gives some at least qualitative things correct. Naively, it shouldn't give anything correct. And for this function f, it's actually not a very good approximation. Yeah, as I said, if you take these ladder graphs, they exponentially decrease instead of going like g. But for the gamma cusp, it's much better for some reason. Yeah, for the gamma cusp, it's much better. But yeah, but it is an ad hoc approximation. It is a.
But actually, you miss already something at 2-loop. I saw that 2-loop that there was only the ladder anyway. You're only doing 4 points, right? And it's always only the ladder. So how can it be that you get some? I saw the ladder was part of the tree, and here I see that it's.
Yeah, but it depends what you mean by. Right, depends what you mean by 2-loop and 3-loop. Yeah, because you are freezing one of the loops. Yeah, so if we are doing 3-loop with freezing one of the loops, which is a 2-loop integral. Yeah, we will miss.
You count. I see. You count 3 loops, but it's 3 loops with one of the momentum that is not.
Yeah. So, yeah, there is some. Yeah, it depends what you exactly call loop. But yeah, but here this is the complete answer for L equals 3, aka 2-loop integral.
It's written.
You are missing the loop. Yeah. So if you are only doing the first 2 diagrams, then yeah, you are missing the loop. So already there, you are missing something. So you might think that if you go to high L, you will be missing a lot and you screw up everything. Yeah, there is no reason why these tree graphs or these ladder graphs should give any approximation of anything, but surprisingly they do. So that's Yeah, but again, there is no reason why one should dominate over the other and so on. They are all of the same order, naively. Yeah.
I have a question.
Yeah.
Sorry, there is one thing I did not understand. So you say that if you resum the ladders and the trees, you get a result as strong coupling, which is of order 1, not G.
Yeah.
Correct?
Yes.
Nonetheless, you get a gamma cusp. I mean, this gamma cusp tree approximation or gamma cusp ladder, which scale like G. So how do you get something that scale like G out of something that is of order 1?
Yeah, but the extraction, I don't know on which slide, the extraction of gamma cusp is not that straightforward. Yeah, so it's not that the first order would correspond to the first order as strong coupling. Yeah, it's not. You have to solve some differential equation. So it's not that the contribution for the gamma cusp at strong coupling would be controlled by the leading order of the strong coupling of this FG. Yeah, it is not that straightforward like that. Yeah, it gets some contribution from the subleading. Yeah, it's not just a pure kind of expansion there. Yeah. So so despite for the F, we are missing the G term completely. For the gamma cusp, we are capturing some of the G terms from the subleading terms from the F. Again, the relation between F and gamma cusp is not that simple. Yeah, so it is not that straightforward. So I don't have any insight what contributes to what. Yeah, it is this formula that I wrote here, which was found in these earlier papers by Fernando Alda, Johannes, and Sikorsky. And yeah, there is some operation that must be done. So for me, it's a little black box how these things are related. Yeah. How the extraction of gamma cusp, what does it really mean? Yeah, where the gamma cusp is sitting in the result. Yeah, so so I don't have any insight. I agree with you. Yeah, it's surprising that despite you are not matching correctly this function of F for gamma cusp, you get some contribution from some subleading terms which actually have the right scaling at the large G. Yeah.
Okay, thanks.
And how do you know the correct boundary conditions to impose when solving equations like this one, or in this other one where you had some recursion for the integrals?
Yeah, there are some boundary conditions. When we solve that, we get from some collinear limit. We know where the function should vanish. Yeah, at some point there is this cross ratio Z. We know how it should behave for Z equals 1. So there are enough boundary conditions. It's not a trivial question, but there are enough boundary conditions to actually fix it. Yeah. Here it's only a function of one single cross ratio, which makes it easy, but yeah, there are some boundary conditions imposed, and yeah, it's a boundary condition for Z equals 1, and then there is also, I think if I remember correctly, for Z is 1/2, or there is some symmetry between Z and minus Z, I think. So yeah, so we can fix it from the boundary conditions just from knowing where the function F vanishes. Yeah.
You have some intuition for the meaning in terms of loop graphs of making this restriction to trees or to
well, it's we have some speculation that if you look at that there is a deformation parameter that you can add to it. There is a natural deformation parameter, let's say Y, which will be raised to the number of loops of these loops. Yeah, so you will deform the whole thing with extra parameter, and the actual amplitude would correspond to Y equals 1, which says that take all graphs equally and sum over all of them. But the geometry somehow wants to add this deformation parameter, say that the loop graphs and the tree graphs are weighted in a different way. Yeah, with this parameter Y. So we were experimenting with that, but we don't know what this Y would mean. You are looking for some analog in integrability, but we couldn't kind of, we don't know. Yeah, but it seems that the real world or the amplitude wants to take all these graphs equally, but they are not really equal from the point of view of geometry. They come from different places. Yeah, one is tree, the other one is loop. despite, again, loop of loops, because formally they are of the same loop order. Yeah, but there is probably also some hierarchy which we didn't see here in the kind of everything as uniform transcendentality in n equals 4, but the functions which appear in these loop graphs have different symbols than the ones which appear in the tree graphs. They have more complicated symbols for people who know what the symbols are. So there is definitely a hierarchy directly in the analytic structure of these functions. Yeah.
Thank you. More questions? Okay, if not, then let's thank Jaros again for a very nice talk.
Thank you.
And so we reconvene for Lawrence's talk in 20 minutes, if I'm not mistaken, or is it 4:30 or 45
in 5 minutes, actually.
In 5 minutes, sorry, 4:30.
Which I think in Zoom is fine to have a short break because there is not much to discuss on in the coffee room. But
okay. Okay, so see you in 5 then.
See you in 5, yeah. Well, Lawrence, actually.
Yeah. Hi.
Hi. Let me actually make you.
Yeah, I'm connecting my iPad. If you could
I need to make you. Yeah. So I need to make your iPad co-host, I guess, not yours.
Yes, that would be useful.
So your iPad has some has your name, or I will see an iPad coming.
Yeah, there is 2 of me and 1 is without audio. So the one without audio is my iPad.
Yeah, you are done. Okay, I see you now.
Yes, that worked. Let me just see. Okay.
Yeah, now it's full screen.
That should be good. Okay, great.
Yeah, I don't remember what Andrea told you but yeah, usually we leave some freedom, right? I tend to say 1 hour first to the speaker because already you see when you say 1 hour to you, oh, it goes over. But
yeah, she told me to give also like 50 minutes of general introduction and then. Like,
yeah, that's right. Yes,
and I think she also told me 1 hour. I can try to.
Because some people announce the time, including the time for questions, and then the speaker usually understands that the time of question can be used for the talk. Which
I'm not planning to, but
okay, good. You don't mind if we put it on YouTube or something?
No, go ahead. Sure, that's.
Actually, I'm still. I thought I stopped the. Did I mess up? Because
it's
now
still recording. Yeah.